As mentioned earlier, the primary objective in this course is to assess the performance of a power electronic converter in terms of the steady state voltage and current waveforms. We have seen that the currents and voltages can be analyzed with the knowledge of switch states, that is whether a switch is on or off, using KCL and KVL. We have also learnt the notion of periodic steady state and some principles of periodic steady state which are useful to analyze the voltage and current waveforms. Quantification of the waveforms is a part of this analysis, and the waveforms are quantified with certain measures. Let us take a look at some well-known measures of periodic waveforms. Some of these measures are used to quantify AC periodic waveforms, some are used to quantify DC periodic waveforms, and some measures are useful for all types of periodic waveforms, as we shall see. Let us consider a periodic function f of t, which represents a periodic waveform, and the period of this function is t, capital T. So that means f of t naught is equal to f of t naught plus capital T for any given time instant t naught. So the average value, as we have already seen in some examples, it is given by 1 by t integral 0 to t f of t dt. Two examples of periodic waveforms are shown here. The blue colored waveform f1 of t is a DC periodic waveform, and the green colored waveform f2 of t is an AC periodic waveform. As seen, f1 of t has a maximum value v plus delta v and a minimum value v minus delta v. It has an average value v, capital V. So it's a triangular waveform with a finite average value. And f2 of t is again a triangular waveform but with a zero average value, with its positive peak being Vp and negative peak being minus Vp. So the average value of f1 of t, denoted by f1 average, is capital V, which is greater than 0. That is why we call it as a DC waveform. While the average value of f2 of t, denoted by f2 average, it is 0. So it is an AC waveform as per the notion of DC and AC in power electronic circuits. Another measure is the average of absolute values, or average rectified value, used typically for AC waveforms. So it is defined as FARV. It is the average of the modulus of f of t. So in this case, f2 is an AC waveform. So f2 ARV is basically the area under the positive triangular portion divided by t by 2, the half of the time period. So that can be shown as equal to Vp by 2. And yet another measure which is quite popular is the root mean square value, RMS value. It is denoted by FRMS. The RMS value of f of t, this function, is denoted by capital F with a subscript RMS, and it is square root of the integral 0 to t f of t whole square dt divided by the time period. So the RMS value of a DC periodic waveform that we considered here, f1 of t, is denoted by f1 RMS, and it can be shown to be equal to v square plus delta v square by 3. And then the RMS value of f2 of t, which is a triangular waveform, it is again a well-known quantity. So it is Vp by root 3, the peak value divided by root 3. And another measure is the peak value, the absolute peak in the case of AC, so which is FPK, denoted by FPK. It's a maximum value of modulus of f of t. And then another measure is peak to peak value, FPP, which is the difference between the maximum and minimum value. So f1 peak is V plus delta V, f1 peak to peak is 2 delta V, f2 peak is Vp because it's absolute peak, and f2 peak to peak is 2 Vp. Here are some more measures. There is something called form factor, which is defined as the ratio of RMS value to the average rectified value. So the RMS value of the triangular waveform, the AC triangular waveform that we have seen, is f2 RMS, which is Vp by root 3, and its average rectified value is Vp by 2. So its form factor is 2 by root 3. And the form factor for the well-known sine wave shown here in purple color, g of t, is Vm by root 2 divided by 2 Vm by pi, which is pi by 2 root 2, which is approximately 1.1. Similarly, a crest factor is defined, so which is the ratio of peak value to RMS value. When I say peak, it is the absolute peak. So for a triangular waveform, AC triangular waveform, it is Vp divided by Vp by root 3, which is again root 3. So form factor and crest factor are mostly used in the case of AC waveforms. And then there is something called ripple factor. The ripple factor is typically used to quantify DC waveforms, and the ripple factor is defined as the square root of RMS square minus average square divided by the average square. So if you look at this, the numerator of this ripple factor is actually representing the unwanted component in the DC waveform. So DC waveform, we ideally want it to be constant, but then we have some ripple. For example, an ideal DC would be this just V, but then we have a ripple over this average value. So that ripple, the RMS value of that ripple as a fraction of the average value gives this ripple factor. So the ripple factor for the DC waveform F1 of t, F1 RF, is 1 by root 3 into delta V by V. So obviously, if this delta V is much smaller than V, it is close to DC. So the waveform having smaller ripple factor is a better DC waveform. Here is another example of DC waveform, which is a rectified sinusoid. It's just the modulus of sine h of t shown here, whose peak value is Vm, but it comes down all the way up to 0. So we know that the average value of this waveform, h average, is 2 Vm by pi, and h RMS is Vm by root 2. So we can calculate the ripple factor as square root of pi square by 8 minus 1, which is almost 0.48. So the unwanted component in this h of t is almost 50% of the average value. It's like 48% of the average value. The next set of waveform measures can be understood by the fact that a periodic function can be represented as a sum of sinusoids. For example, let us consider the square wave shown in red color here. The square waveform is shown in red color here. This square wave can be seen as the sum of different sets of sinusoids. So consider the first set. In the first set, which is shown in the very first plot, there is a sinusoidal function S1 of t shown in green color, and there is another sinusoidal function which is S3 of t, which has a different amplitude when compared to S1, and its frequency is 3 times that of S1. So when we add S1 and S3, we have a blue color waveform, S1 of t plus S3 of t, and that is how it compares against the square wave. Now consider the second set. What are we doing in the second set? We are adding yet another sinusoid, S5 of t, to S1 of t plus S3 of t. And it is important to note that S5 of t has another amplitude, in fact a lower amplitude than that of S3 of t. And in the third plot, we are adding another sinusoid, S7 of t, which is not shown here, but the resultant waveform S1 plus S3 plus S5 and S7 is shown again in blue color, and we can say that it is a little closer to the square wave. Then the fourth plot shows the resultant function when 5 sinusoids are added. If you start adding more and more sinusoids at appropriate amplitudes at different frequencies, we'll see that the resultant waveform becomes more and more close to the square waveform. So in the first plot here shows when sinusoids up to the 11th multiple of frequency are added. Now the second plot shows the resultant when sinusoids up to 13th multiple are added. Then the third plot is when the sinusoids up to 15th multiple are added. And finally, if you include the sinusoid up to the 21st multiple of frequency, the waveform looks like this. So it can be observed that as the number of frequency components in the sum are increased, the resultant waveform becomes closer and closer to a square wave. In other words, a square wave can be seen as the combination of sinusoids at different frequencies. The same is true with any other periodic function. It is important to note that only a specific combination of sinusoids in terms of magnitudes and frequencies can represent a given periodic function. In fact, it is a unique combination. Before we learn how to arrive at the combination of sinusoids, let us try to understand why is such a representation of periodic function important. It can be explained like this. The AC voltages and currents should ideally be sinusoidal, but in power electronic circuits, the AC voltages and currents are not necessarily sinusoidal. So, if we can represent the non-sinusoidal voltage or current waveform as the sum of sinusoids, we can clearly distinguish the desirable and undesirable components of the AC waveform and quantify the closeness of the AC waveform to its ideal counterpart. Given a periodic function, how do we split it up into different sinusoidal constituents? What are the frequencies, amplitudes and phases of the sinusoids that are present in a periodic function? These questions are answered by the well-known Fourier series. A periodic function f of t with period t can be expressed as a sum of sinusoids as shown in this equation. F of t is equal to a naught plus sigma n is equal to 1 to infinity an cos n omega t plus bn sin n omega t. This is known as the Fourier series expansion of f of t, and an and bn are the coefficients in the Fourier series expansion. The periodicity of f of t can also be expressed in terms of phase angle in radians, as it is convenient to deal with angles when trigonometric functions are involved. The phase angle corresponding to a time instant t naught is omega t naught, where omega is 2 pi by capital T. Thus, the time period of t seconds becomes equivalent to 2 pi radian. So the coefficients can be calculated by these integrals. A naught is equal to 1 by t integral 0 to t f of t dt, and an is 2 by t integral 0 to t f of t cos n omega t dt, and bn is equal to 2 by t integral 0 to t f of t sin n omega t dt. And these integrals can also be written with the integration variable being omega t instead of t. So then the limits will change to 2 pi or 0 to 2 pi. It can be noted that the first term in the RHS, the right hand side of this equation, the Fourier series, is the average value of f of t. That means a naught is equal to f average. And the second term on the right hand side, which is the first term in the infinite sum. Okay, the first term in the infinite sum is the first harmonic of f of t, and the first harmonic of f of t is also referred to as the fundamental component of f of t and is denoted by f1 of t. So, and f1 of t is expressed as a1 cos omega t plus b1 sin omega t. Considering the square wave as an example, the red color waveform shown here, f of t, and the green color waveform f1 of t is also shown here, which is the fundamental component of the square wave. It can be observed that the fundamental component has the same frequency as the original periodic function. And what is the RMS value of the fundamental component? It is expressed as the square root of a1 square plus b1 square by 2 and denoted by capital F1 RMS. Similarly, the second term in the infinite sum, on RHS is the second harmonic component of f of t, and the third term in the infinite sum is the third harmonic component, and so on. The nth harmonic component of f of t is denoted by fn of t and is expressed as an cos n omega t plus bn sin n omega t. And the RMS value of the nth harmonic component is given by f n RMS is equal to square root of an square plus bn square by 2. As an example, a third harmonic component is shown here. So in purple color, f3 of t. So it has the frequency 3 times that of the fundamental component, and its amplitude can be calculated as square root of a3 square plus b3 square by 2. Consider the square wave as an example. Here the square wave has Vm as positive maximum and minus Vm has negative maximum. So the average value of a square wave is 0 as it is known, and the RMS value of the fundamental component, that is the RMS value of this green color sinusoid that is drawn, is f1 RMS, and by calculating the Fourier coefficients it can be shown that it is equal to 4 Vm by pi into 1 by root 2. Similarly, the RMS value of any nth harmonic component of the square wave can be shown to be equal to 4 Vm by n pi into 1 by root 2. So in the case of a square wave, the RMS value of any nth harmonic component is just 1 by n times the RMS value of the fundamental component. This is a very interesting result. Having known the magnitudes of different harmonic components, we can plot them against the frequency. So one example here, a generic example which is shown here, is Fn RMS versus n omega. This plot shows the magnitude of each harmonic versus a particular frequency, omega 2, omega 3, omega and so on. Such a plot is known as a harmonic spectrum. The harmonic magnitudes and frequencies can also be normalized with respect to the fundamental and plotted as a harmonic spectrum. For example, here we show the harmonic spectrum of a square wave, where Fn RMS divided by F1 RMS is plotted against n. N is the ratio of the harmonic frequency to the frequency of fundamental component. So if we consider the fundamental component magnitude as 1, it will be 1 because it's normalized. So if it is 1, then the third harmonic will have a value of 1 by 3, fifth harmonic will have 1 by 5, as expected by the expression Fn RMS is equal to F1 RMS divided by n. Based on the Fourier series expansion, the RMS value of f of t can be expressed in terms of its average value and the RMS values of individual harmonic components as shown here in this equation. So FRMS is the total RMS value of f of t. It can be written as f average square plus f1 RMS square plus f2 RMS square and so on under square root. So if we know the RMS values of different harmonic components that are present in a given periodic function, we can evaluate the complete RMS value of the function. The Fourier analysis helps us arrive at certain measures for AC periodic waveforms which are widely used to evaluate the harmonic distortion in those waveforms. So for an AC periodic waveform f of t, the average value is 0. So the RMS value is simply the sum of all the harmonic components, f1 RMS square plus f2 RMS square and so on. So the RMS value of the fundamental component is denoted by f1 RMS, and the RMS value of the ripple component. What do you mean by ripple here? Ripple is a collective term. The frequency components of f of t other than the fundamental component are collectively referred to as ripple. So the RMS value of the ripple component of f of t is square root of f2 RMS square, f3 RMS square and so on, and is denoted by f tilde RMS. So in other words, this ripple component is something that is unwanted, undesirable. So the ratio of RMS value of the fundamental component to the total RMS value. So how much is the fundamental component in comparison with the total RMS? So that is defined as the distortion factor FDF1, which is equal to F1 RMS divided by F RMS. And the total harmonic distortion THD in a periodic function f of t is defined as the RMS value of ripple divided by the RMS value of the fundamental component. This THD is widely used to assess the closeness of an AC periodic waveform to sinusoid. So if there is less THD, that means a given periodic function or periodic waveform is close to sinusoid. The numerator in FTHD, F tilde RMS, can be calculated by subtracting the mean square value of the fundamental component, that is F1 RMS square, from the total mean square, that is F RMS square. So thus the THD can also be related to the distortion factor FDF1 as shown here. THD is equal to square root of 1 by FDF1 square minus 1. Considering the square wave as an example, which is shown in red color here, and the square wave has maximum value of Vm, positive maximum Vm, negative maximum minus Vm, and its fundamental component is shown in green color. So the RMS value of the square wave is just Vm, and the RMS value of the fundamental component of square wave, which is the RMS value of the green color sinusoid, is given by 4 Vm by pi into 1 by root 2. So from these we can estimate the THD. So the THD of a square wave is about 48.43%. What does it mean? It means that the ripple component of square wave is as high as 48% of the fundamental component. As we have observed, determination of Fourier coefficients is essential to evaluate the harmonic distortion in a periodic waveform. The calculation of Fourier coefficients involves definite integrals over the complete period of the waveform, and therefore certain waveform symmetries will be useful to simplify the calculations. If a waveform has even symmetry, all the coefficients Bn will be equal to 0, while the coefficients An will all be equal to 0 when the waveform has odd symmetry. Examples of odd and even symmetries are shown here. The odd symmetry is shown in blue color and the even symmetry is shown in green color. So odd symmetry refers to the condition f of minus t is equal to minus f of t, while even symmetry refers to the condition f of minus t is equal to f of t. The calculations can further be simplified if a waveform has half-wave symmetry. It is defined as the condition f of t by 2 plus t is equal to minus f of t. That means the values of a function repeat after half time period but in a negative manner. Consider the examples here. One triangular waveform in red color is shown whose peak value is V peak. So the values repeat after half time period but in a negative manner. So the triangular waveform has half-wave symmetry. Now you consider the sawtooth waveform, which is shown in purple color. So it is periodic but it is not half-wave symmetry. Why? Because it does not satisfy this condition f of t by 2 plus t is equal to minus f of t. Consider the value at t equal to 0. The value of this sawtooth waveform at t equal to 0 is minus V peak, but the value at t by 2 is 0. So there the condition is violated. So this sawtooth waveform does not have half-wave symmetry. But if a waveform has half-wave symmetry like this red color triangular waveform, then the coefficients, Fourier coefficients An and Bn, can be evaluated by merely integrating over half period. So now the integration limits will be changed to 0 to t by 2 as opposed to the original case of 0 to t. That is how the calculation gets simplified. The calculation of coefficients, Fourier coefficients, becomes even more simpler if the waveform has quarter wave symmetry in addition to half wave symmetry. This quarter wave symmetry is a condition within half wave symmetry. So f of t by 2 plus t is equal to minus f of t, and f of t by 4 plus t is equal to f of t by 4 minus t. So consider this triangular red color triangular waveform, so where which has half wave symmetry, and then now if you define this t by 4, 1/4 of the time period. So if you look at the waveform, it has same values on either side of t by 4. Either side of t by 4 the waveform has same values. That refers to quarter wave symmetry. And similarly the quarter wave symmetry is also applied in the negative half cycle. But you consider this waveform, this brown color waveform that is shown here. Why it does not have quarter wave symmetry? Because if you consider two time instants which are equidistant from t by 4, which are on either side of t by 4, but the function does not have the same value at both the points. That is why it doesn't have quarter wave symmetry. But if a waveform has quarter wave symmetry in addition to half wave symmetry, like this triangular waveform, then the Fourier coefficients can be evaluated by simply integrating over 1/4 of the complete period. That way the calculations will be further simplified. The variable of integration can also be changed to omega t instead of t for convenience when dealing with trigonometric functions. So this table shows the integrals written in terms of omega t as integration variable. Let us try to understand the use of these symmetries for simplification of calculations. Let us consider square wave as an example, and we are interested to find the RMS value of the fundamental component of this square wave. So let us try to observe the square wave, whether it has symmetries or not. So it has odd symmetry. That means f of minus t is equal to minus f of t. That means all ans will be 0, a1, a2, everything will be 0. And then half wave symmetry. It also has half wave symmetry because f of t by 2 plus t is minus f of t. If you take a value here in the positive half, you will find the negative of the same value after t by 2 interval, which is in the negative half. And it also has quarter wave symmetry, where f of t by 4 plus t is equal to f of t by 4 minus t. So if you look at equidistant points from this t by 4 instant, they will have the same value. And so since a1 is 0, f1 RMS will be simply b1 by root 2. Now b1, how is b1 defined? It is 2 by t integral 0 to t f of t cos omega t dt, or you can also integrate in terms of the angle. So I am trying to do in terms of angle. So 2 by 2 pi integral 0 to 2 pi f of t cos omega t d omega t. Since the waveform has half wave symmetry and quarter wave symmetry, we don't need to integrate all the way from 0 to 2 pi. It is enough if we integrate from 0 to pi by 2. So we rewrite the expression for b1 as 2 by pi by 2 integral 0 to pi by 2 f of t cos omega t d omega t. Then from 0 to pi by 2, this function has constant value vm. So by substituting that value in the place of f of t and carrying out the integration and applying limits, we can show that the RMS value of the fundamental component of square wave is 4 vm by pi into 1 by root 2. So that is how the calculations get simplified by the use of waveform symmetries.